Hello everyone. This lecture of dynamics of the lithosphere is the fourth part on elasticity and regional isostasy. In the previous lecture, we've studied the flexure which is induced by the emplacement of a laccolith inside the Earth crust. So, as a starting point, we had the master equation for flexure in which we neglected the term P. We integrated this equation 4 times to find W, the deflection, as a function of x. That's the solution we obtain after applying 4 boundary conditions. And with this solution, we could make some predictions about the displacement, the strain, and the stress field also inside the bent plate. This week, we want to apply this equation to study the flexure of the lithosphere, and the starting point will be similar to what we had in the previous week. So we have the master equation with the fourth order differential equation, and we will be looking for W. So the question is, what about isostasy and the lithosphere? So if we want to study this case, we need to introduce the concept of isostasic restoration force. So let's consider this sketch here. You have a lithosphere here, and it is a case which is before the loading of the plate. So the plate here is flat, and there is here water at rest on top and a fluid mantle below. So we have an elastic plate here, and after the loading, the plate should be deflecting downwards. So now, in the middle, we assume there is W, an addition, deflection. So the water column has increased in height. So we compute the weight where the load is being applied. So the weight is the thickness of water times the density of the water times G, plus this extra thickness W. We also have the thickness of the plate, H, times the density of the plate, times the gravitational acceleration. We also compute the weight away from the load. So away from the load, in this blue column, we have, in fact, thickness of water times density of water times G, plus, if we go down to the same depth here, we have density of mantle times thickness of the plate plus this extra thickness, which is nothing else than W. So we have this expression. To compute the upward directed hydrostatic restoration force, we need to make the difference between these two pressures, basically. So we compute this minus that, and we simplify it to get minus density of mantle minus density of water times G times W. So that is the net contribution of the force. So remember, in the master equation, we have the term Q. This restoration force needs to be added. So we will have QA, which is the load which is applied, and this is the reaction pressure that is induced by the resulting configuration here. So we can add this term into the equation. We can place QA on the right-hand side and move that term to the left-hand side, and we end up with this equation. So now let's consider the case where the lithosphere or the mantle lithosphere is overlain by continental crust. So the density now is rho c. Let's assume now we have orogeny, and now there is an extra thickness of W of crust in the middle of the model, while on the side of the model, we will have an extra thickness of mantle, if you want to compare the two columns, of thickness W. So if we repeat the exercise for the case of the origin, we simply end up with the same expression as before, except that the density here is the density of the crust. Nice. So that's the equation we now want to deal with. So for the lithospheric flexure case, we will solve this equation, but we'll use an alternative strategy than what we did in the previous case. We will now use some intuition to solve this equation, and we will guess the solution. We'll use a solution ansatz. So that's what we're going to do. First, we are going to assume a shape and a magnitude of the load, QA. That's an expression for QA. QA would be density of the crust times G times the thickness of the crust. But now the thickness of the crust varies with X. And we assume a sinusoidal variation of H. So we have the maximum value, H0, and it varies with periodicity, sinusoidal periodicity. So QA can be expressed as rho CG H0 times sinus 2 pi x divided by lambda, where lambda is the wavelength. Second, this is where we use an educated guess. We will use a periodic solution ansatz. And that is that's basically the solution. W is W0 times sinus 2 pi x divided by lambda. So, as we say, it's even more than intuition here. What you can do with this solution ansatz, you can introduce it in this equation, and we can try to solve for W0. So you notice that this solution ansatz has the same periodicity as the load. That's part of the intuition which is being used here for finding a solution. So let's inject this ansatz into the master equation. So we combine the two equations. The load, the periodic load, is included here, and we inject W with a periodic variation in all of these terms. For the time being, we can set P equals 0 again. And what we want to do now, once this has been substituted here and there, we want to solve for W0, the maximum deflection. So after some algebra, which you will have to do as part of the exercise, you get this expression. So this expression gives you a relationship between the maximum deflection, W0, H0, the maximum thickness of the load, the ratio of the density of the mantle and the crust, the flexural rigidity, and an important parameter here, the lambda, which is basically the wavelength of the load. So lambda is a wavelength and it has unit meters. Now we have this expression, and the question is, what will happen if lambda is very small? So if lambda is very, very small number, this division will become a very large number. So this term will start growing. As this term grows, this division tends to 0. So W will tend to 0. What does it mean? It means that the lithosphere does not deform in reaction to this load. So if lambda is very small, the lithosphere will not deform. And we can deduce that it is effectively rigid. So a load that has a very small wavelength will not deform the lithosphere, because this term, which contains the rigidity, will become dominant in the expression of W0. Now let's consider the opposite case. What happens if lambda is very large? So if the wavelength becomes very large, this ratio will become very small. So this term will tend to 0, and W will tend to rho c times H0 divided by rho m minus rho c. And this now should ring a bell. So does it bring you any memory, this relationship? It should, because this is the expression of that we used in the isostatic equilibrium lecture. So in the first exercise, basically. This is how we computed delta H, which was the isostatic rebound due to variation of columns, adjacent columns. So that is a limit that our model should also capture. So that's very interesting, because when the loads are distributed over large areas, which means lambda is very large, they become isostatically compensated. The deflection will become the same to that of the Airy isostatic case. So our model, the flexural model, can capture two end members. The case where the plate is effectively very rigid and does not deform. So if lambda is very small, but it can also capture the end member where the plate deforms with negligible rigidity. And so now I should say a few words about the effective elastic thickness, because that's a term which is being used a lot. So remember, the main parameter of the rigidity of the flexural model is the rigidity. The rigidity has h to the power 3 here, where h now is the thickness of the plate. So in this idealized model, we would have an elastic plate on top of a fluid mantle. The exact thickness of the elastic lithosphere as such is not well known. And in fact, a sharp boundary between elastic mantle and fluid mantle is unlikely. And a smooth transition is rather expected, because we have thermal gradient through the Earth lithosphere. So we should rather expect to have a smooth transition between elastic and fluid mantle. There should be a fictitious layer of finite thickness that would produce the equivalent elastic response if this system is flexuring. So this equivalent thickness is not something you can really pinpoint, but it's the response that matters. So this thickness here is what is called the elastic equivalent or effective thickness, TE. It is just a substitution of H by TE in this equation. So the flexural rigidity of the lithosphere will be proportional to elastic thickness to the power 3. So for the periodic loading of the lithosphere, you get to do some exercises in the notebook, and you get to practice a bit. So you will have to impose a periodic load on the lithosphere, where h here is the height of the topography. And you will assume a periodically loaded lithosphere, where the model domain will vary between 0 and lambda. The amplitude of this maximum topography will be 1,000 meters. You compute the Moho depth using a local area model and the given parameters here. And you'll do the same with the flexural model. So with the flexural model, you need to evaluate D, you need to evaluate W, and you need to W0, and then you can compute W, knowing W0. For this, you get extra parameters, and you'll be able to then model both flexural isostasy, so the regional model, and airy isostasy, the local model. So for this, you can write a function, so you will be working on a function. And one thing which will be important is that as an input, the x coordinate, we will always scale the x coordinate by lambda, the wavelength. So this is a scaled input. So we'll be working with x divided by lambda. So you study the role of the elastic thickness on the Moho profile, and you vary the elastic thickness in a range of parameters, and you get to study how to discuss what you observe. And you will also study the role of lambda on the Moho profile, and you try different wavelengths, and you should also discuss the results. You should obviously capture the two limits that were discussed in the lecture. So with this, I will conclude the lecture on regional isostasy, and I think I can congratulate you, because now, once you've done the exercise, you will master the concept of local and regional isostasy. You know how to visualize these solutions, and additionally, you know how to derive it too. It should be in the lecture notes now. So based on this, I'd say congratulations, and see you next week.